Okay, then I'm going to start. Okay, hi everyone. I'm Thailand from the Technical University of Darmstadt, and I'm going to introduce our simulator Elastisim for batch system simulations for malleable and evolving workloads. So let me start with some introduction, some background. So on resource and job management. So usually resource and job management systems like Slurm, for example, they schedule jobs and they provide resources in computing environments such as HPCs, clouds, etc. And often called job schedulers, batch systems, and mainly they have different objectives. So some objectives might be more system relevant, like system efficiency. The other objectives might be user perspective, like job completion time, minimization. And usually you have a mix of both, which the schedulers target to reach in the long run. And the decisions are usually taken in the scheduling algorithm. So this is the key component making that decision. So you also heard a lot of malleable jobs, etc. And I would like to classify those jobs shortly because it will be relevant also for the presentation. So Feidelson and Rudolph have classified the jobs in 4 different types, and it basically boils down to who decides the number of assigned resources at which time. So classically, you might know rigid jobs. So this is when the user has a number of resources requested, and at submission time, this number of the resources are assigned and not changeable during runtime. This is a rigid job. If the system is able to flexibly change that number at submission time, we call them moldable jobs. And if the system is even able to change that during runtime, we speak about malleable jobs. But there's also a 4th type of jobs, so these are called evolving jobs. And evolving jobs are essentially when the user or the application can make requests during runtime to change the number of resources of the application. You might also see that evolving and malleable jobs are often classified as adaptive jobs in the literature. Okay, so here's also a short diagram. So you can see on the left side, there's a rigid job. The time and resources are fixed in that regard. Moldable jobs in the center, you can change the resources in the beginning, but not during runtime. And an adaptive job will be able to react to resource changes during runtime. Okay, so if you want to evaluate scheduling policies now for these kind of jobs, you could do experiments on a real system, but usually they are quite expensive. They will consume a lot of time. They are very resource intensive. They might introduce system threats, and of course, it's not available to everyone because you cannot just simply rent a supercomputer to test out your scheduling algorithm, and no administrator will allow you to do that either. So in that regard, you have to stick with simulations at some point anyway. So simulations are usually faster. They produce reproducible results. They are independent. You can change your constraints like platform design or different parameters of the system. And of course, it's resource efficient in the best case. So now coming to what Elastisim does or what it is. Essentially, it's a simulator for the simulation of jobs and applications. The batch system itself, so like we have a simulation instance that simulates the behavior of a Slurm, for example, Maui torque, and we support rigid jobs, moldable, malleable, and with a new update, we also support evolving jobs. And the simulation of the scheduling algorithm is also integrated, and we have the platform powered by SimGrid. So it's a flow level simulator. I will introduce that in a short second. And a typical use case, if you want to use our simulator, so we live a little bit outside of the live framework. We're more kind of a tool that where you evaluate results in before. A typical use case is evaluating a scheduling algorithm when you want to have a scenario with the combined scheduling of all job types, for example. Okay, so let us start with workload modeling first and why we need that. Usually, if you want to simulate applications, workload modeling is crucial since the reliability of the platform simulation will depend on the executed workload in the environment that you simulate. And if you choose a non-representative workload, that might lead to some inconclusive results, and in the end, your results will not be anything you can probably publish anywhere. So workload modeling is therefore a crucial part and is the responsibility of the user usually. And what we we studied some workload characterizations, and usually they indicate that workloads, they tend to alternate between phases. So if you have iterative applications, for example, at some point you might do checkpoints, and before that you might have compute phases, and at some point you have I/O phases. And this is a classic a pattern we see often in workload characterizations. So therefore, we have proposed a workload model that comprises jobs and application models. And essentially, so on the right side, you can see the so our workload structure. So a single workload, in our case, a scenario, comprises a set of jobs. So, and each job holds properties. So things like the number of resources, maybe priority, submission time, etc., and an application model. So this application model is the crucial part for the simulation. They represent the simulated application. So we divide that into phases and tasks. And tasks, as you have maybe heard before in the presentations, we support performance models so that you can describe the load that is actually put or introduced into the platform that you can describe that with a single performance model. So coming to performance models, or how they would essentially look like and what it represents in our case. So it's essentially a human readable mathematical function. And what we use performance models for are so with that we can allow the application to configure or reconfigure during runtime and the adaptation of the resources. So a performance model can give you the possibility to describe the configuration of an application or the application for multiple configurations. This is the idea behind performance models. So you can use XRP, for example. We will have a presentation not after me, I believe, but later on. And you can use tools like XRP to obtain them, or sometimes even inspecting applications will suffice. So a simple performance model, so just for demonstration purposes, would be if you want to describe a computational task, you can just simply take the floating point operations and divide them by the number of compute nodes. You would get some kind of a linear speedup, but that's not very realistic. So therefore, with these performance models, you are also able to introduce some non-linearity. So you can put the number of floating point operations, you can divide them by the number of compute nodes to the power of 0.85, for example, so that you get kind of a non-linearity and more realistic results in your performance models and the tasks. So coming back to the application model. So the application execution model here on the right side, you can see from top to bottom, we have multiple phases, and every single phase has, of course, multiple tasks. And you can see already that this follows some kind of a building block approach. And for these tasks, you can see on the right side, we provide multiple task types that we can simulate. So this can be a computation task, a communication task, it could be an I/O task, but compute and communication is also something that you can combine. And each of these tasks, they have a payload. So this payload, this introduces the load on the simulated platform. So this might be something like bytes to communicate. And in the payloads, you can use a performance model. You don't have to, but you can use a performance model. And in the end, these performance models, they will essentially boil down to a single number. So you can describe the bytes to communicate or the bytes to write. And in the end, this will be evaluated during runtime. You get a single number, and then in the end, you can just simply distribute them using payload distribution patterns over the resources. So, for example, if you have a compute task and you want to describe the floating point operation, you can describe them for the whole task, for all resources, and then you define a pattern like only the root, for example, should currently do the computation, or it should be evenly distributed. And for communication tasks, you have distribution patterns like master-worker principle or evenly distributed, so that all-to-all communications occur, etc. So this is the application execution model. And the most important part on the right side is essentially that we use these phases. So we could have otherwise used only tasks, but we use phases and tasks because for malleable jobs, we introduce the scheduling points exactly between the phases. So if you have two phases, you will get a scheduling point automatically integrated, if you do not specify otherwise, between two phases. And this is a safe point where, for a malleable application, you can actually reconfigure the application. So this might be something like after a checkpoint, for example, at some kind of a barrier. For evolving jobs, I will also come to that later. This is also a possibility that you can describe an evolving request exactly before a phase starts, so that an evolving job is able to describe the number of resources it would like to have for this next upcoming phase, for example. Okay, so coming to that, so we have a new update with the evolving jobs. It's just a couple of weeks old. Essentially, so evolving jobs, they are able to request resources during runtime. We let the user specify that separately for each single phase. So essentially, if you know that you're coming into a very compute-intensive phase, you might want to have more resources. And an evolving request has an implicit scheduling point, and it will always invoke the scheduler. So in that moment, when the scheduler is invoked with an evolving request, the scheduler is still able to reject or even alter the evolving request, or it can simply accept the request, and then the number of resources will be assigned to the job at that point. So like we have it with the payloads for the task, for evolving requests, we can also use a single number or a performance model. So once again, you can take a function like number of nodes times 4, which will essentially mean that the current number of resources that are assigned to the job should be taken times 4, so that we can expand in the next phase, for example. So what we also have is we have a fifth type of job. We call them adaptive jobs, that essentially combines the feature of malleable and evolving jobs. In that regard, you can describe applications that might have phases that do not have any evolving request but a scheduling point, so that you can expand and shrink by the premises of the scheduler. And you might also introduce an evolving request for a specific part where the scheduler has to be invoked, and then in that moment has to make a decision based on the suggestion or the request of the job. Okay, so going to the architecture of Elastisim, I would like to shortly introduce some platform simulation background. So usually state-of-the-art frameworks, they are discrete event simulators that model networks, and they use either a flow-level approach or a packet-level approach. So what you can imagine is packet-level simulators, they model every single packet in the network, and as you can see, this can get quite resource intensive, as there are a huge number of packets that are being fired as an event in the discrete event simulation. So therefore, a good alternative is usually that you have flow-level simulations. And flow-level simulators, they define network communication as some kind of a flow that communicates between different sources and sinks, and it consumes available bandwidth. So essentially, if you have, in this graph, for example, a communication going on between A and D, it would be completely fine between those two routers. But if now C and D, for example, introduces a new communication, you will see that in the middle between those two routers, you will get some kind of a congestion, and this, in that regard, is then modeled as a flow between those two routers. So what we do, or what we employ, is the flow-level simulator SimGrid, which is essentially our base below Elastisim for the discrete event simulation. Okay, so I would like to give you a short architecture overview. So essentially, we have Elastisim, first of all, takes user, from the user some inputs. This is the platform, the SimGrid platform. We have the workload that you describe as jobs and application models. And of course, configuration, things like when do we invoke the scheduler or other metadata information that you might want to give to the simulation. So in the end, you get simulation results and outputs. And what's happening in between is that you also provide a scheduling algorithm. The scheduling algorithm is a process that lives outside of the main simulation process, and it communicates via inter-process communication. So each time the scheduling algorithm is invoked, you will make a decision on the scheduling process, and that will be forwarded to the simulation process. And you can also see on the bottom the simulation engine. We have the SimGrid core, and then some simulated hardware like disks, hosts, CPUs, etc. Also compute nodes, everything that is in bold text is semantics that we introduced or we put upon SimGrid. And then of course you have actors like job submitters that simulates behavior of users, for example. The batch system itself, compute nodes that communicate with the batch system, a monitoring module, and the actors look essentially something like this. So you have the batch system in the middle, and the job submitter is essentially submitting the jobs, reading the workload file. You have then the platform that is managed by the batch system. All the nodes, they report their state so that the batch system is able to invoke the scheduling algorithm at certain times. And after the schedule has been decided, the batch system gets that again, and the monitoring module is taking care of monitoring every single hardware and platform you have. Okay, so the scheduling protocol in our simulations are usually either periodic or event-based or both. So you can define an interval if you want to have a periodic invocation, or you can let the scheduling algorithm invoke on job submissions, finalizations, scheduling points, etc. So evolving requests are mandatory. You can also have a scheduling point post reconfiguration. So you have multiple triggers to trigger the scheduling algorithm. And when the algorithm is invoked, you will usually get the job queue, the state of each compute node, and some system metrics. So this might be the simulation time or some utilization of the system, etc. And what we also support is the progress of a single job. So each job usually reports its progress, which we define as the number of completed phases and the number of total phases, so that you might be able to also create progress in the scheduling algorithms. We use that for deep learning, for example. So we have also a storage model with semantics for parallel file systems and node local burst buffers for especially so as we use them quite a lot in the Admire project. Parallel file systems are quite simplistic, and it's a dedicated. These are dedicated I/O nodes behind a single namespace. So I/O tasks will always have the affinity to these I/O hosts, and will then simply write their bytes onto those. And we also have node local burst buffers. They come in two flavors. We have exclusive access, or you already heard of different file systems like GeckoFS, for example, before, and we have Beyond, etc., where you have a wide striped access, and you can essentially have a single namespace for all the node local burst buffers behind this namespace that then also aggregates the storage space and essentially combines all the different burst buffers on the node, so that you have that you can simply use that without distinction and in a non-excluded way. Okay, so also we have a GPU model. We especially use that for deep learning applications. We support multiple GPUs per compute node, and the user specify the performance like they do in SimGrid platforms with the CPU. And also, what we also let the user specify is the bandwidth, and the GPUs are fully connected in our simulations. And if now you have to, for example, have communication between your different GPUs, Elastisim will automatically detect which GPUs are not on your node, and will automatically introduce the intra and internode communication. And so, yeah, this essentially also sums up more or less the work. So as a summary here, it might be some unique tool for malleable and evolving jobs for your scenarios, which you can use. We have a website, so you can click on the website or simply scan the QR code. The website has also a Slack invitation, so feel free to join the Slack. We are currently building up more and more also the community work. Everything is also on GitHub. We're public and open source. And if you want to contact me, there is my email address. And this also more or less, does conclude my presentation. So thank you very much. Okay, any questions?
One question for the bus buffers.
Yeah, sure.
These bus buffers you have, can be deployed on any node, or
We have that always on the job itself. So if a job has specific nodes, you can only use the nodes, but you can only use the burst buffers on those nodes.
And we can apply the burst buffers on different phases of the application or not? Or they should be applied to all the phases of the application?
Currently, currently they are job-wide, and during the whole application, they are always assigned that. So one thing which we also should maybe mention is for I/O tasks usually. So as I have introduced with the platform simulations and the flow level semantics. So flow level semantics, they of course they have it's simplistic in their way how network communication occurs. This might be very fine for network communication if you have MPI communication for InfiniBand, Omnipath, and when the nodes are communicating with each other. For I/O, this can, of course, sometimes cause interferences and different metrics like packet sizes might also be something that is very, very important for I/O tasks. So, of course, with flow level simulations, because we base everything on SimGrid, I/O tasks have a certain limit in their degree of freedom, let it put it that way. So that you cannot maybe define every single aspect of I/O. But if you would do that, at some point you would be at packet level simulations again. And if you need an HPC to simulate an HPC, that's somehow this is not the purpose of the simulator, folks, because we are mainly focused on scheduling. But yeah, this is something that we support in that regard. Yeah.
And it's possible to define more variants for the access. I mean, other policies for data distribution, not only exclusive and white stripes.
We could introduce something like that. This is the current solution. So what do you have in mind, for example? So I think
I don't know. For example, in Hercules we have random access. For example, we have has distribution depending on some things.
Yeah, so I mean,
there's like a function to define this kind of access, or has to be mapped in the simulator right now?
This is currently in the simulator, but as every single model is essentially modularized, so we can usually so these white striped and the exclusive ones, they live in separate places, so that you could extend that. So that would be possible.
Thank you.
David? Yeah.
Yes. As you know, we are end users of Elastisim. So based on our experience, we have a very large number of jobs, and we need to do many repetitions. The simulation time sometimes is quite large. So I'm just curious about if you have considered developing a parallel, maybe it's already parallel, I'm not sure, but or faster version of the simulator. Using, I don't know, multi-cores, distributed GPUs, is it possible?
So yeah, this is a very good question. So I'm not sure if you have maybe tried out the latest versions a couple of weeks ago. So there was a
not
huge,
me, but maybe you, maybe I don't know.
Maybe so there was a
not me.
Yeah, no problem. There was so this is also something I can maybe for the users that were using it a couple of weeks or a month ago. So we had a huge performance upgrade. So it was like we had scenarios where which took hours before that are now concluded in minutes. So there was a huge performance upgrade on that regard. We also put a new scheduling trigger, which was also suggested by the University of Kassel, one of our power users currently, that we also might be able to trigger the invocation not periodically if you need it all the time, but after a reconfiguration occurs, for example, so that you can immediately react when the job is coming into a scheduling point, reconfigures itself, and frees up resources, for example. So before that, you had to look always periodically if some nodes are free or not. So this is also something that we put on, so that will save a lot of time. And I also read in the Slack channel that we had a huge performance upgrade for their scenarios. So it might be worth checking out. Currently, we simulated a couple of thousands of jobs on 1,000 nodes in a matter of 2 minutes or something like that. So it can really help with the newer version.
What do you do besides optimizing this part?
So first of all, multi-core and multi-threading is a little bit for discrete event simulations, they can get a little bit tricky. Sometimes you might sometimes one thread might advance in time, and then you have some problems with having things happening in the past which should have reflected also in the future. And also we're bound to a certain degree to SimGrid, of course, and SimGrid is already very good and optimized in that regard. What we did was we drastically reduced the number of actors. So compute nodes were actors before, now they are passive actors, but not SimGrid actors anymore. And of course, we had the scheduling protocol changed. So what is always taking a lot of time is communicating between the scheduling process and the simulation process. The scheduling process lives in Python usually, which is not a problem. But if you use the inter-process communication via 0 and Q, then you have to exchange data through the inter-process communicator. So this is quite fast, but if you do it a lot of times, so for example, every 30 seconds like Slurm does for a month, then of course it adds up at some time. So we had there a lot of performance optimization so that only modified nodes and modified jobs are being forwarded. And so we essentially kept out every unnecessity to improve the performance. We can also have a short chat later on maybe. And so yeah, that helped quite a lot in that regard.
Good news.
Okay, then thanks again, and yeah.